To draw the Lewis dot structure for the sulfate polyatomic ion, we're going to need to know how many total valence electrons exist in the ion. So to start off with, the formula for sulfate is SO4 with a 2- charge. That means that every sulfur is bringing in 6 valence electrons, oxygen is bringing in 6 valence electrons, but because there's 4 of them, they're going to bring in a total of 24 electrons. Add those together. And then this 2 negative means that the compound added 2 electrons, so we need to add that to our total charge. So 6 plus 24 plus 2 gives us a total of 32 electrons that we will be working with when we draw out this compound. I'll move that aside for now. All right, we know that our central atom is sulfur based on the fact that we have 4 oxygens. So we'll start by drawing out sulfur in the center. Then we're going to attach with a single bond each oxygen atom to that. We're now going to add in all of the remaining valence electrons around the oxygens, fulfilling each oxygen's octet. When we go back and count, each atom has a total of 8 electrons in its valence shell, and sulfur's octet is completed. And therefore, this is one potential structure for the sulfate polyatomic. In order to determine if this structure of the sulfate ion is the most commonly formed, we're going to need to assign formal charges to each of the atoms in the compound. So to start off with, formal charges, as we've calculated them before, are calculated by taking the number of valence electrons each atom has and subtracting out the number of assigned electrons. The most stable configurations are those that have the most zeros. Zooming in on our sulfate ion here, we're going to calculate the formal charge for sulfur to start off with. So sulfur comes in with 6 valence electrons, and it currently has a total of 1, 2, 3, 4 assigned electrons. So we're going to subtract that, and it gives us a total charge of a 2 positive. Each oxygen is identical, so once we've calculated the formal charge on one oxygen, we'll know the formal charges on all of the oxygens. Each oxygen comes in with 6 valence electrons and has a total of 1, 2, 3, 4, 5, 6, 7 assigned electrons. So we're going to subtract 7 assigned electrons from that, giving each oxygen a total charge of -1. I'm going to add those in, -1, -1, -1, -1. Again, our sulfur we said was a 2 positive. Well, the good thing about this is that we know that the total charges of all of the atoms have to equal the overall net charge on the polyatomic. So if we were to take a look at this, the overall net charge we said was a 2-, which we do end up getting from our 4 oxygens being a 4-, and then our sulfur being a +2. That's not the only configuration, however, that can occur for this polyatomic. It's also not going to be the most stable. With this being a +2 right here, it's telling us that there is potentially another version that we could have. So let's take a look at what else we could do. All right, we're going to look to see if there is another structure. Oftentimes we call these resonant structures for the sulfate ion. I'm going to quickly sketch back in our original drawing where we had 4 singly bonded oxygen atoms around that central sulfur atom. As I'm doing this, I want you guys to be thinking about the fact that sulfur is actually located in the 3rd row. And as we've talked about in class, what that allows us to do is to actually violate the octet rule with sulfur. And if we can do that and also reduce the charge of the formal charge of sulfur, then that is likely going to be the most stable conformation of the sulfate ion. So if we were to actually eliminate these electrons and then add in double bonds, The oxygen atoms are not violating their octet. They're still fulfilled. Sulfur has that expanded octet, but let's go ahead and calculate the formal charges on each of these atoms just to make sure that what we've done is actually legal. Okay, so again, looking at sulfur, it's going to, again, still come in with 6 valence electrons, but now we have to look at how many assigned electrons it has. So it has 1, 2, 3, 4, 5, 6. That gives us a formal charge of 0. One of the things we like to see in our Lewis structures is lots of zeros with formal charges. All right, if we look at our oxygens that are double bonded, and again, these are going to have the exact same formal charges. So we have 1, 2, 3, 4, 5, 6. Oxygen comes in with 6 valence electrons and has 6 assigned electrons. That gives us a formal charge of 0. So we have zeros on here. That's looking good so far. As we had already noticed from before, that the oxygens that are single bonded have 1, 2, 3, 4, 5, 6, 7. They came in with 6. They now have 7 assigned electrons. The formal charge is going to be a -1. We have 2 of those. And that's going to be the most stable conformation for the sulfate polyatomic. So we're going to go ahead and put our brackets around that, put that 2 minus. And while that was quite a bit of work to actually get there, hopefully that makes a little bit more sense why sulfur can actually have an expanded octet, and therefore why sulfate is going to more likely be this as opposed to the one that most of you drew for your quiz answer.